Okay. Hello, everyone, again. Good afternoon. This week we have again another graduate from our department, Osman Tursun. Osman Tursun is currently a PhD candidate. Actually, he defended his thesis recently successfully at the School of Electrical Engineering and Robotics in Queensland University of Technology in Australia. His current research interests include large-scale image retrieval, image restoration, weakly supervised learning. He received his bachelor degree from computer science from the University of Science and Technology of China and his master's degree from our department. And today he's going to talk about large-scale image retrieval, and this is an important problem for us, and some of us are working on this, so we are looking forward to this presentation. And thank you, Osman, for joining with us. And the screen is yours.
Thank you for the introduction, and thank you for this great opportunity to present my work with you. Today I will talk about the missing ingredients in optimizing large-scale image retrieval with deep features. So this is my outline. I will quickly cover content-based image retrieval and its application, challenge, and the deep image retrieval and the existing research gaps I find during my PhD studies. And then later I will talk about my works I have finished during my last 3 years PhD. It's about attention-based approach and the learnable test time augmentation for CBIR and efficient knowledge distillation framework for zero-shot sketch-based image retrieval. So content-based image retrieval is searching similar image based on the visual content instead of tags or codes. And this is like a classic diagram of CBIR. It has two main modules. One is feature extraction, and another is feature matching. Content-based image retrieval has many applications such as face recognition, person re-identification, and etc. And it has some main challenges. One is like a semantic gap, and if you look at this image, and from human perspective, the query image can be panda, but for machine, it might be just 5 black circles. And it also has some geometric illumination variance challenges. And also domain difference. Query and the gallery can be different, and they can be from different domains. And the last one is the request on the high scalability, accuracy, and efficiency. Although through the many years, content-based image retrieval has been studied very well, and many problems has been solved, but still some problems are still remaining. And if you look at the milestone of CBIR, before 2030, global features are widely used, such as shape and texture and color. Those features are very efficient, but their accuracy not enough. And later, aggregated local features has been applied for such as sift and surf with combination of bag of words, VLAT, and a feature vector. This approach is good for detecting a local similarity. However, they have a complex pipeline, insufficient accuracy, and a limited scalability. And from 2014, after the success of AlexNet, deep features has been used for CBIR as deep neural networks learn general features through training on the large scale image data sets such as ImageLab. And currently there is the two main schemes for deep CBIR. One is the off-the-shelf features, another is fine-tuned features. So initially, off-the-shelf features are used for CBIR. The features are extracted from the fully connected layers and then applied with some post-processing such as normalization, PCA whiting. And this approach get comparable results to the previous handcrafted features. And however, people find fully connected the features from the fully connected layers are very specific to the training data set. So people the researchers find convolutional mid-level convolutional features has more like general features. So, however, the problem is convolutional features has like large dimensions. So pooling approach has been applied before extracting features, and so one is like extracting max pooling from the each channel of convolutional features. Another is like using the sum pooling instead of max pooling. Another approach is RMAC. This is the advanced version of like max pooling. Instead of extracting one single max actuation, this one extracting multi-scale max actuation and then aggregate to single features. So this one is like a more robust to scale difference. People also apply attention to enhance some important features before pooling, such as numerical attention. These CRO methods apply spatial weighting and the channel weighting based on the feature maps and the sparsity of the channels. Another alternative approach is generating this attention based on the most activated classes using class activation maps. Those are the off-the-shelf features, and another scheme is like fine-tuned features. For fine-tuned features, initially like a classification-based method are applied, but these methods require semantic labels. Another approach is like using the metric learning. So triplet loss is widely used as it's trying to put closer similar images and put away dissimilar images. The alternative of triplet loss is contrastive loss and the quadratic loss. In quadratic losses, like we have like one more negative like samples, and some research results showing quadruplet loss is outperformance than triplet losses. And now I will talk about some research gaps I found during my studies. The first one is deep features are not so robust to some background clutter or unimportant regions. Another one is deep features are not robust to geometric transformations such as rotation. And the third one is the features might fail out of distribution cases such as zero shot. And to combat these three problems, I studied a visual attention-based approach. So with visual attention, the features, we can extract the features from the most salient objects. And for combating geometric transformation or illumination variance, the data augmentation approach might be useful. The third one is to combat like zero-shot cases. I applied knowledge distillation approach to transfer general knowledge from a well-trained network to the student network. And to study those approaches, I apply our proposed approach on the three tasks. The first one is trademark retrieval. We test our method on the meta trademark data set. It's the biggest data set. It has 1 million trademarks with 417 queries. And the second task is landmark retrieval. It's a well-known task for CBIR community. So it has Oxford and the Paris data sets. And the third one is sketch-based data set. It's different from the previous two data sets. As you see, the query and the gallery are actually from the two different domains. And for sketch-based image retrieval, I use Qctro, Tuberlin, and the Sketchy data sets. And for evaluation, I applied normalized average rank. And so the smaller value means like better ranking results. Another is mean average precision, and a high MAP value representing the good top N results. And now I will talk about the contents, the work I have finished during my PhD. This part including like 3 modules: attention-based approach, and test time augmentation, and efficient knowledge distillation frameworks. And I will starting from the attention-based approach. The first one is component-based attention for large-scale trademark retrieval. As you see, the features tend to fail because of background clutter and unimportant region. And this one, if you look at this picture, like this one, the left is our query, the right is 5 images are top 5 results. However, these results are not so good, and we find the features fail because the text similarity in these logos, but for trademark retrieval, text similarity or font type similarity are not important. To combat this, we propose soft attention and hard attention approaches. And our hard attention approaches are very simple, and it's a very it's a very simple approach. So we just remove the text from the original logo and then send to the neural network. And so in this case, neural network will not confused by the features from the text area. And to detect text, like we propose unit-based pixel-level text segmentation approach, and then we applied handcrafted in painting, and then we use auto-crop approach to crop the figurative regions. And these are examples of before text removal and after text removal. As you see, after text removal, we not only remove the text, we also can fix the scaling problem as well. And another approach is soft attention approach. Unlike hard attention approach, in this approach, we want to enhance the features from the figurative elements in the feature space. To this, we apply an attention before pulling the convolutional features. And the question is how we can get these attentions. To this, we apply convolutional activation map. Convolutional activation map is a weakly supervised approach. We can localize this objects, just learning to classify those objects. The objects in the data sets. And to this, we trained a neural network to classify a logo is a text or figurative text. But after training this neural network, we can generate soft attention as this example. So as you see in this here, these red regions are corresponding to the text and the blue regions corresponding to figurative elements. By using this attention, we can enhance the features from the figurative region. And if we look at our results on the multimedia data set, those blue results are other deep learning or handcrafted features. And this yellow and the red is our result. And as you see, our hard attention and the fusion of the hard attention and the soft attention is getting the best result. And our soft attention actually is better than other soft attention approach, except for RMAC. And we will come back to this later. In overall, we get good results. And if we look at some individual examples, as you see, without our attention, the expected results is not in the top 10 results. And if we compare our results with previous work on the Matthew trademark data set, as you see, our results are getting the best result with the less dimensions. So our feature is also very efficient. And so the contribution of this work is we propose the salient component-based attentions. And in last work, I show our hard attention methods is getting very good results. And also we found our hard attention we also found the main solution for the hard attention is text removal, is also useful for image editing and the privacy and the image translation problem. So we studied this text removal problem as a separate problem. So text removal approach, text removal is also studied problem. Previously, it's only dealt with handicrafted in painting, but those methods only work for some like a solid background like images or other digital image. Later, deep learning approach applied for text removal. And the early text removal approach is proposed by Nakamura et al. It's a very simple approach. It's just a patch-based autoencoder. And later, John et al. Proposed a GAN-based approach. And the problem of these two approaches is they have limited scalability because those approach can be trained on the large scale text data sets, real images. As you know, like text detection is also very hard problem. In their approach, they are combining both text detection and the removal in the single approach. And so it's very hard to training these data sets on the real text data sets. And another problem is like less interpretable. So we don't know like whether a failure case is caused by the poor text detection or poor in painting. And also it's uncontrollable. Once we send the image to the neural network, it will remove all the text. And it's also not general. So if the model trained on the English, it's not useful for Arabic or other Chinese texts. And so for combining all this problem, we propose mask-based approach. Like we send a mask as a condition by controlling the mask. We can control the in painting. Now also we reduce the burden of the text localization. However, the problem here is we will depend on third-party text localization method. To avoid this, we consider this text localization as a mask refining. So in this case, we not only can utilize third-party masks, but also can remove text without them. So, for example, in the no third-party mask cases, we consider like we sending the network as a full mask, and this mask will be refined to the very fine mask. And to get high recall mask, because we ensure like the text area always under the mask. Okay, we use a Tversky sky loss. This will ensure high recall and assure and the high precision. And to get better in painting, like we propose like a two-stage in painting, coarse in painting and a fine in painting. And for training over these two networks, we use like a generative adversarial loss and the perceptual loss and style and the weighted L1 losses. And also we also, to control the in painting, we also transfer the attention from our mask refine network. So let's look at our whole framework. So our framework is composed by three parts: this coarse in painting branch, and the fine in painting branch, and the mask refining branch. And in the middle of the coarse and the mask refine branch, we have attention branches. And so these attentions will help to locate this text. Text will be helpful for text localization. And so we trained our methods on the largest synthetic text localization data sets, and also real text removal data set, SCUT data sets. And to evaluate our in painting results, we use some evaluation metrics used for evaluating image quality, such as MSC, PSNR, and SSIM. And we get the state-of-the-art results on the SCUT dataset with the less parameter. As you see, like our network has only have 80 million parameters, but it gets the best results in SSIM and the MSC score. And this one is our like method on the general cases. Like although our method is trained on the English text, but it can also useful for removing some Japanese text or Chinese or Bengal text. And also this one is the case for controllable text removal. So like, by controlling the mask, we can control the where we want to remove. And we did ablation study by sending a perfect or coarse or full coarse mask. It's corresponding to missing case. And so as you see, like without our mask refine or attention branch, the results actually dropping. And this one is like a visualization of our attention blocks. As you see, we have like 4 attention blocks. And so the first 2 attention blocks is focused on the text area. And next attention blocks are focusing on the background area, as it's like as same as like our suppose like we first trying to, in the early stage of inpainting, we want to focus on the text area. Later we want to like focus on the background areas. And so the contribution of this work is we propose a mask guided inpainting and the mask refined network and the mask attention and the coarse and the fine inpaintings and other new learning objectives. And this work are published as the like ICTAR and the CBIR. And the third one, another work is a learning regional attention over multi-resolutional deep convolutional features for trademark retrieval. And as I mentioned before, our soft attention methods are not as good as RMAC. RMAC is a kind of like a pooling. It uses like a multiple scaling before max pooling. However, there's some problems in RMAC. It's using max pooling. This might cause loss of information. To solve this problem, we apply both max pooling and the sum pooling, and then like, we merge them. However, we use PCA whitening after merging, so we will not increase our feature dimension. The second problem of the RMAC is it's not so robust to multi-scale. So we use multi-scale like inputs. And the third problem is RMAC also fail when background clutter or trivial regions exist, as there's many small scale like windows exist. And there's already one like work have been dealing with this problem. Like they propose attention-based approach, and however their attention-based approach is like a supervised approach, and their regional attention network is trained on the ImageNet. That might be different from the over like target data set. So it has two problems to dealing with. Like we propose unsupervised attention. Okay, we consider each window as a word, and we calculate their frequency. We use the reverse frequency as the attention for this windows. So this is like our whole framework. So so we have 3 contributions: multi-resolutional input, and the mix and the sum pooling, and the unsupervised regional attention. And so we compared our result with other off-the-shelf features and handcrafted features and the fine-tuned features as well. So in overall, like we get very good like NAR and MAP results just using 256 dimension features. And this one is our qualitative results. So as you see, like we can retrieve very good top 10 results with this feature. And we also did ablation studies. So our ablation studies shows like our all of our 3 contribution, introducing incremental improvements to the trademark retrieval. And so the contribution is like a mix pooling, mix and sampling, multi-resolutional input, and unsupervised soft attention. And this paper is accepted by ICIP 2021 today. And so this I have finished the work regarding like attention-based approach. Now I will talk about learning test time augmentation for content-based image retrieval. And as I mentioned, these features are not so robust to geometric transformation. And then, for example, in this case, like we expect this sketch apple and this red apple should be closer in the embedding space. However, like they might be, but the reality might be not like that. And so we also did other experiment regarding this matter. So in the meta trademark data set, even these subtle differences such as contrast difference or these circles or rotations can change the ranking and the distance values. And so it's very hard to train a perfect convolutional neural network that can combat like various different type of geometric transformation or illuminations. However, it's very easy to getting different different types of different augmented types of the input image. And we suppose if we aggregate features from different augmented types of input image, we can get more robust features for robust features to geometric transformations or other variants. And the question is how we can select the best data augmentations. Like as we know, like we have like so many different kinds of data augmentations. And to this, we manually selected 16 popular data augmentations, but still it's like a large data augmentation pool. And so for this, to further decrease the number of data augmentations, we apply reinforcement learning. And here we have a control based on the RNN. It will randomly sample n data augmentation. In our case, n equal to 8. And after that, we apply this data augmentation to our image, and then we can calculate the contrastive loss and also our transform diversity loss to generate rewards for the controller. By training this control, the control learn to choose the best data augmentation to the trademark retrieval. And to increase our diversity of the learned data augmentation, we propose the diversity loss. It increased the number of different types of transformation and also their properties. And to speed up this training, we propose feature catching pipeline. Here we only extract the feature in a single time and cache them. So this approach speed up the whole training process about 100 times. And we test our approach on the landmark retrieval data set and the trademark retrieval data set. And we test the transferability of our approach. Our approach is trained with VGG network with max pooling. However, we test our approach on other pooling such as RMax, Spoke, and the Crow. And as you see, this green part is the improvements we get with the learned data augmentation. And also we test our transferability on the different network. We test the ResNet, DenseNet, AlexNet. As you see, we get lots of improvement with our learned data augmentation. And this one is a visualization of learned data augmentation for trademark data set and the landmark data set. And so we learned different data augmentation with different properties. And this one is one of our qualitative results. The first row is the results without any data augmentations, test time data augmentation. The second row is with data augmentation. And the second result is very interesting. As you see here, actually we capture the rotation difference, rotation, and also contrast difference. And so the contribution of this work is learnable test data augmentation and diversity loss and the offline feature caching. And the last work I will present is efficient knowledge distillation framework for zero-shot sketch-based image retrieval. And So in this work, we propose an efficient framework for zero-shot sketch-based retrieval. And so zero-shot sketch-based image retrieval is searching image with sketch instead of a real image. In the classic SBIR task, all classes are seen to training. However, in the zero-shot sketch-based image retrieval, some classes are not seen by the neural network during the training. And there's two main challenges in the zero-shot sketch-based image retrieval. One is like a domain shift. It's same as classic SBIR. Another is zero-shot cases. To dealing with domain shift, people using metric learning with separate backbones for the special feature layers. And this will increase the computational cost during the training and the inference stage. To dealing with a zero-shot problem, people are using language model, transferring this general knowledge from the language model to the visual model. And these methods require semantic labels, and it requires a trained language models. And also the common problem in zero-shot sketch-based image retrieval is the training framework is so complex, it's not like efficient. Like for example, here, this is one of the state-of-the-art approach. It's using like two different backbone for two different domains, and also using like a generator adversarial network to mapping this visual embedding and to the common embedding as a language model. So it's so this training process is so expensive. It's hard to train. To combat this problem, again, we propose an efficient framework for zero-shot sketch image retrieval. The first contribution is we only use a single backbone for both real domain and the sketch domain. Another our contribution is we propose domain-aware quadrant loss. Here we introduce one more negative from the sketch domain, and this not only improves the improves the retrieval results, but also solves the domain imbalance problem. And the second contribution is we also introduce identification loss. And the third main contribution is we propose an efficient knowledge distillation. It doesn't require any semantic label, as we generate this knowledge only by extracting average visual embedding. Instead of like using the language model, we are using the visual model. And also this process is only offline single time. So this process only done one time. So it's very efficient. So we use this our knowledge as a soft label to train the network. So this is like our overall loss, and it's like it's a combination of our knowledge and the class losses and the similarity losses. And so we test our method on the sketchy and the two Berlin data sets. And as you see, like we get like a very good state-of-the-art result with an efficient feature. Our feature dimension size is only 512. And we also ablation studies on our three learning objectives. And as you see, all three learning objectives introducing incremental improvements. And this was our qualitative result. Like we choose some best result and some worst results. And as you see in our best result, like we reach you all our top 10 results are the correct result. And but even our worst result, as you see, like we are reaching very a reasonable result. As you in this case, this one is like a cat, but actually it's returning tiger. It's a false result, but it's reasonable because, as we know, like a tiger is as an animal also belong to cat families. And so the contribution of this work is 3 learning objectives and also efficient knowledge distillation process. And the conclusion is, so for improving deep image retrieval performance, okay, we propose attention-based approach, it including soft and hard attention. And for dealing with geometric transformation, we propose learned test time data augmentations. And for zero-shot cases, like we propose efficient knowledge distillation approaches. And these are our reference. And thank you.
Thank you, Osman. That was a very nice presentation with a lot of content. So you tried to squeeze all your PhD in a short amount of time. Any questions from the audience? Okay, maybe I can start. So the test time augmentation, learnable test time augmentation, in the slides I don't remember seeing a comparison with standard augmentation. So can you comment on that? How much improvement you obtained over standard augmentation?
You mean the train data augmentation, training time data augmentation?
No, just without using any, just using standard augmentation. Not the learnable augmentation, but standard augmentation, you know, flipping, cropping, etc.
Yeah, like we haven't done it, like because yeah, we haven't compared that one. So because there is no such standard data augmentation for test time, like there is some like it's just like flipping, only like a horizontal flipping, but we haven't compared with that one. But like in our like training, we have flipping data augmentation, as you see, like a horizontal flip, and the horizontal flip actually didn't bring any like improvement during the training.
Okay. And I was curious about Tversky loss. Am I pronouncing it correctly? On slide 6.
Yeah. So this is, if I go. So we use this loss. I will show this framework because we are like giving a mask to the our fine in painting branch. We want to this mask always like it covers the text region. So for this, like the recall is very important. So this Tversky loss ensure high recall. Meantime, also assure like a high precision. So it gives priority to the recall first, and then increase the precision.
Okay, so this is an alternative to dice loss, for example, for
yes, yeah. It's actually some a little bit modification of dice loss, or maybe generalized version of the dice loss.
Okay. Okay, this is the first time I see this, so it's interesting. So okay, with the weights, then you control it to have more importance on recall.
Yeah, by controlling alpha and the beta value, like we can like make it to give like a more like priority to recall. So like during the training, like we actually get like a 100% recall.
Okay, very good. Any questions from this Hande?
Yeah, so I have a couple. I don't know how much sense they make. One is for the logo retrieval. So I was wondering, like, because, like, for example, some kind of font for logos can be quite characteristic. Like in the case of Facebook, for example, they have their own kind of very familiar font. So I was wondering, like, have you, maybe I missed that part, have you also considered in like using the detected text, like using the detected text also for logo comparison and maybe adding that into results, or like does it give better results just to like ignore that text information completely, or can it be like in case maybe if the font is copied, especially for logos with only font, like not without text, without kind of other image in a sense.
Yeah,
Like,
that's a very good question. Actually, you are very correct. Like sometimes, like a font is also very important. Actually, during my presentations, there's some missing part. Like, if it's like a pure text logo, actually we keep it. Like we said, like we are removing. But if it's like pure, we are keep as it as a text.
right.
So this text only removed for the figurative logos.
Right.
And but that approach is like a little bit of my early work, and so it's a better like way to do dealing with this, like separating the text and the logo separately, consider both features, and yeah,
Right.
it might be a good feature work.
Right.
Yeah.
The second one is, so I was interested in with it, like the diversity of the images that you retrieve. Like for example, for the last part, like the sketch-based retrieval, you seem to have able to retrieve like diverse type of photos. For example, there was one butterfly with like both of the wings showing in the sketch. I think that was in the first slide or something.
Yes.
So the query
Yeah.
image, here, the first one. So the query image is like, it shows the both kind of wings, but the retrieve images are like from the side, like showing kind of like one wing. So I was wondering like if it makes sense at all in this application, or if you have considered to kind of control the diversity of images retrieved, like images from like that are similar to the query image, but maybe images that are also like kind of different from each other, so as to like propose different options to the user in a sense.
That's under the category of fine-grained sketch-based image retrieval. This one is like a general sketch-based retrieval. It's mainly like considering this class level, like so it's not under the but there's other like a category. They are focusing on this problem, like it says that is like a fine-grained sketch-based image retrieval.
Right.
Yeah.
But you have done some kind of diversity-based search. At some point, you were pointing to a diversity loss. So I was like,
oh, that's the data augmentation part.
Yes.
This part, this one is here. Like we are trying to like, because we learned like this data augmentation on the separate data set, small scale data set, test them on the large scale data set. So because in the small scale data set, maybe some of the data augmentation are actually sufficient enough to get very good result.
Right.
So our like agent, this agent will be only focusing on those data augmentation. It will not choose other data augmentation.
Right.
So that's why we are trying to like force our agent to choose as much as diverse data augmentation, so it can has some generality in the general data set.
Right. Yeah, I see.
Yeah.
Well, in any case, like a lot of work, like well done on like a lot of work, a lot of information, a lot of different topics, like well done. It was really like
sorry
a very
confusing.
There was a lot of content. Thanks for the presentation.
Thank you for your question.
Any other question? Otherwise, we can stop the recording and continue informally. Okay. let's do that then. Okay, Osman, thank you again. That was very nice.
Thank you so much for listening.
Nice presentation and nice discussion, and we will continue informally after the recording. Okay.